Okay, welcome everybody. For this week's session, topic is 3D log and the digital twin. I'm Eki Zwicker, Global Head of Robotics product line. With me is Moritz Oettinger. He is the Global Product Manager for Robotics.
Hi, everyone.
So let's go to the next slide. Let's step into this. It's about 3D log technology. One remark, if you have a question, just type it into the comment and we can address these at the end of the session, but really feel free to drop questions already during the session. Now, 3D log enabled robotics inspection, the drivers. I mean, first of all, it's worker safety. That means avoiding human entry in hazardous and dangerous areas. So that's the robotic piece. What is coming then to 3D log? It is about automation. That means having gathering reliable and repeatable high quality inspection data. Firstly, and secondly, taking then these data with the position where the data has taken. That means building up the digital twin. So these are the main three drivers. The second two, automation and data, is related to 3D log. Let's continue having a closer look into confined space inspection. So from confined space entry to robotics, what we see here on the left side is the classical way of doing it. It's an inspector in the vessel. That means you have confined space entry. You need to prepare all the assets for human entry. You have manual reporting. The only upside is the human intelligence. That means the capability of a human kind of interpreting already what he sees and taking actions. The next step was camera on a stick. That means you're putting a camera on a stick and you put it into the confined space. You're avoiding by design the confined space entry, but you cannot reach all spots. That means you have limited access and limited reach. You have manual operation. You have unstructured data. You're gathering tons of data. You have it on your SD card, and that's it. And then you need to create a manual and report manually. Nowadays, robotics is used for visual inspection in confined spaces. It means you avoid all the confined space entry, no blinding, no scaffolding, all these advantages you have with robotics, and full access, you have the full reach. However, I mean, it's still manual operation. You operate the system manually. You need to look from outside where the robot is. You're getting unstructured data. Again, you're capturing data on the hard drive. It's questionable how you can repeat the inspection, and you need to create a report again manually. So that's basically where we are. And where we're heading into is 3D log as the enabler for digital twin. That means this technology provides a full 3D spatial awareness of the robot in the asset. That means it makes the operator easy to operate the robot without line of sight. It's interactive, and then all inspection data is automatically tagged with the precise position in the asset. And by this one, we are creating a digital twin containing all the inspection data. So three advantages: we have localization, we have we have the exact position of the robot in the confined space. We have navigation, full 3D spatial awareness of the robot in the asset, and digital inspection data is automatically geotagged to a digital twin. So that's the digital twin in overview. Let's have a look at the process, how typically this is executed. In order to start, you need to have the asset in 3D. There are three ways of getting to this. First one is the first option is you have the data already in 3D. You can use existing CAD data, load this then into 3D log. The second option is you have assets without any drawings or 3D model, but then we have capabilities for what we call 3D dynamic reconstruction. We can have a look at this small movie, giving an insight in this one. You're putting a LiDAR scanner into the asset. You're collecting a point cloud in the first step. This is what we see here. Then you can cut out the areas of interest. That's the second step. And then the third step, what we'll see here, is then meshing it, creating a surface model from this asset. This is what we'll see here in the next shot. With this one, you have captured the 3D environment automatically, and you can use this data then later on for doing the inspection. And the third option is a dedicated tool for creating pressure vessels. It's called the Asset Builder. We can have a look in this one now. So it's a little bit like a specialized CAD tool for pressure vessels. Easy to operate with drag and drop. You see it here. You're selecting the diameter. You're selecting different typical features you have in a pressure vessel, like vortex breaker, like valves, like buffer blades, like all the nozzles and main entries. And this data can be loaded later on into 3log. In between, we have the planning and simulation. Next step is to go through a full inspection planning, either using API standards or company internal procedures. You can do feasibility checks. You can do mission and inspection planning. You see here a little screenshot of a simulation tool by which we can load the robot virtually into this vessel, and using our hardware, control hardware, to maneuver then this virtual robot in this virtual vessel in order to check the feasibility of inspection, in order to train and to rehearse an inspection. The motivation behind this one is to do as much as possible already prior to the inspection, so that at the end you just go on site and execute the inspection. And that's then the next step. We have the robot executing. We see right now here the mission execution. If you play this movie now, mission execution. See here the operator operating the bike robot driving into a pressure vessel. You see here then the 3D position of the robot in the control. So that's a view from the navigation camera, and in parallel you have all the time the 3D pose of the robot in the control. And that's here right now tagging the inspection data to the position. Each shot, each picture is tagged automatically to the position. You can add comments, you can add findings. It's just some impressions from operating the robot in the vessel. Some close-up views on points of interest. In this case here, vortex breaker. And again, taking the shot and tagging it to the position. Same works for ultrasonic data. You can have ultrasonic measure, and you tag it then to the position, and then driving out. So that's the mission execution, what you have seen here. Out of this, we are generating then the digital twin. We will have a live demo done by Moritz later on this one. First, we want to have a look at the SLAM, simultaneous localization and mapping. I hand over to Moritz for this one.
Yeah, well, this is a pretty new functionality as far as the bike robot is concerned. A rotating laser range finder on the robot basically creates point clouds while the bike is moving or while standing, and simultaneously localizes the robot in this unknown environment, so that the point cloud output is a consistent map of the environment. What you see here in the movie is a test run in our office. I will later also show how that looks in an actual pressure vessel. It's basically showing how the mapping is done, moving, then stopping for a moment to create a undistorted map extension using the LiDAR. The point cloud is only the starting point. At the end of the point cloud generation, there is another step that is basically creating a mesh model that then can later be used for 3D lock, for basically localizing even a robot that does not have a rotating LiDAR. So basically, a robot with purely localization features can then be also operated in such a map. As you might notice, this movie is sped up. The actual process is slightly slower, but nevertheless, it saves a lot of time because you don't have to do the modeling step up front. Here you see the bike going into an actual pressure vessel. you see a little bit how it looks inside. And now this is a sequence of the point clouds that the robot generates while moving through the asset. And as you see, all these clouds, they have gaps. There is stuff missing, but they also basically create new areas that were not covered before. And the whole data set is then registered into a one consistent point cloud showing the entire pressure vessel. The last step is the meshing step. This is the point cloud. It still has some artifacts, a bit of the robot cable, and also some other traces. And then the meshing step converts this into a useful map of the environment, which can then be used to localize the inspection data, localize the robot, and do a full 3D log inspection. So I will now go ahead and show you how the data then later can be represented, how it can be analyzed, and basically what you gain from this technology. In this example, we focus on a mission that was done using the bike robot. The basic technology also works with other types of internal asset inspection systems. So this is the mission viewer interface. The first step would be to load the mission database that was collected during the mission. It loads fairly quickly. The database contains all captured information, all the images, all ultrasound readings, or any other measurement technology that was used during the mission. I will quickly remove a few things to focus on the essential stuff. So first of all, we have the asset itself. It's basically the 3D model that was used. This is a model that was pre-generated. It's not one coming from a SLAM process. That has the advantage that it features details also on the outside. Obviously, it has to be done upfront. In X-ray mode, we can look through it. It's a pretty empty asset. Now, if I go to the normal visibility and I cut into this asset, we can look inside. And then basically here on the bottom, we have a full timeline of all the missions that were done in this asset. Every mission itself is one of the gray highlighted blocks, and all the colorful icons here represent captured data that where the operator decided to basically record an image or any other type of data. Every gray block is basically a restart of a mission or a new deployment of the robot. So if we go here on that second big block and now enable the view of the robot, we can see that basically I can slide this now. The robot goes in through the manway and then starts driving around in the asset. It's really the entire timeline. So basically all robot positions are stored, and especially where data is captured, there is a little highlight here. We can also show the camera cone for visual inspections. That is very interesting to see. Basically, that shows where the camera was hitting, basically here at this nozzle and the area that more or less was contained in the image. Now, if we are at such a capture, we can, on the right-hand side, we have some basic information about the mission that was entered by the inspector. That can also be modified. Tools used and customer information, asset information. But now if I go on the capture, I can basically see this is the photograph that was taken by the inspection camera at exactly this location. We also have details about the picture itself, for instance, what zoom level and what light settings were used, and all these things. Also, some other information is captured, like the bike navigation camera images, a view of like what the operator had in view in the 3D when he took the shot, and there could be other information like a screenshot that the operator later wanted to use, and some imported images as well. So this is basically what you have at each of these data points. They have different colors for different type of instruments used. For instance, the green ones here, that is ultrasound thickness readings, but essentially it's the same. It shows where it was taken. I can rearrange this a little bit to better see like where that was done. The robot is on top. It's over here where the robot is. Ultrasound does not is not measured with the camera. It's really just where the robot is. And in the captured data, you see that the operator attached the ultrasound scan data and also a thickness reading of 29.2 millimeters. The tool also allows to highlight things, so the operator can choose to mark important captures with a star symbol. That's basically just by clicking here. Usually these are the ones that later go also in the report. The operator has a flag he can set if the data, if the inspection data should appear in the report or not, but no data is ever deleted in this mission. When you see how the bike is moving around, another important thing to know about it is basically where it really went. So we have a way of showing the trace the robot did during the inspection. So this orange path basically shows the trace of this deployment. If I go to the next one, it will make the path a little dimmer and only show the path of the current mission. In this pressure vessel, the bike was inserted a couple of times for various reasons. One reason was also a change of inspection tools, which we can see here in the last one, where basically we have a different color of markers. These are markers for a special tool that does surface profiling. I think we can see that here. On the imported image, we can see some analysis of the surface structure and corrosion. So the missions can be extended and they can also be relaunched a day or two later. No data is ever lost and everything is stored in 3D. Now for providing this to a customer, the software allows various exports. A simple export is to export the images, basically choosing a folder, and it will export the images. It allows to choose what type of images. We can also export the data, basically into a CSV format. Also here we have a choice of what data we want to export. If we give a file name, we can do that. The most commonly used export, however, is the generate report function. If I click this and assign a file name, it will create a report with all the findings that were marked that they should go into the report. That report is in the form of a Microsoft Word document, and obviously then the inspection company can also customize this Word document using their own template. So let's just have a brief look at how a report could look like when only the important findings are in the report. All the other stuff is still remains in the mission database. So you see here, the document has useful templates for revisions, tracking. It comes with a table of content and also a summary page where basically the mission information is entered, but the operator or inspector could also again here enter new mission information if they wanted to. And then for all the findings, there is an overview. It lets the reader know like which capture it was, so to find it again in the mission database, and the description of it and recommendations. And then we see the findings themselves. They all come with, for instance, a visual finding comes with the image captured, the 3D view, and as well the distance that the robot had traveled, some coordinates of the bike, where the camera was hitting, and includes also the description. There are also imported images. So for instance, here an external camera was used, showing the same location. They were added later to this finding just to make sure that all the context is there. The report continues like that. Every finding has all this information and all the imported data as well. So for instance, these are calibration checks. For instance, I guess in the back we will have thickness readings, a summary table showing all the thickness readings done, and also some calibration data. So it's a pretty complete report, and typically the inspectors would then take this, add their personal flavor to it or whatever that is needed, and hand this over to the customer together with the database file, which allows the customer also to verify that and see if they didn't forget anything important. So now let's go back to the presentation. So conclusions and takeaway. The whole 3D log technology is not just an inspection technology. It starts with that. It starts with localizing a robot, and with the robot, the data during an inspection inside a confined space, and basically helps the operator already to execute the inspection. It continues by creating and also maintaining a digital twin of the asset. The basis of that is the mission database. It contains time-stamped data, location-stamped data, and it allows for full context of how the data was collected. It then goes further on with generating the report into a Word document, which is very fast. It's automatic. No manual work is involved there, at least to the extent of creating the report. And it's also customizable so that inspectors and end users can modify the report according to their needs. And then, that is one of the most important parts, the cycle starts over. The inspection can be repeated at exactly the same locations, because obviously the 3D log allows the robot to return to the locations that it gathered the data initially. I think with this we can conclude this presentation. In case there are any questions in the comment section now, we are here to answer them if we can, and I guess we should leave the stream open for half a minute or so if some questions are there.
Yeah, while waiting, if you want to learn more, you see here the link to our homepage or to our website where you can find all the data about the 3D log technology. If there's no question, or if there are no questions, I mean, no problem to reach out to Moritz or me later via LinkedIn or via our website with your questions, and we're happy to provide you an answer on this. If you want to have a demonstration or if you want to have a deep dive on this one, please feel free to reach out to us and we will give you a deeper insight. So there's one question about Single time can be fixed the UT module and visual module. It can be used both in parallel. That means we have the UT and the camera on board, and we can execute both in parallel. Thank you very much. Okay, good. I think we can come to an end. Thank you very much for attending. I hope you got an idea of the 3D log technology and the benefits. And as already mentioned, if there are further questions, if you're interested, please feel free to reach out.